are discussing about the concepts of wave optics for JEE. In fact, we know optics is mainly taken in two parts. One of course is geometrical optics and one is physical optics or that wave optics. And this particular chapter mainly deals with the wave nature of light. Not only that, considering the wave nature of light, how to explain the concepts of interference, diffraction and polarization. These are the major topics of this particular chapter. We in fact know, according to Huygens wave theory, light is in the form of waves. In true sense, he has predicted the waves as longitudinal waves, which do require material medium to travel. Without the medium, they cannot travel, and all we all know. But at a later stage, taking the concepts of Maxwell's electromagnetic wave theory into consideration, Huygens wave theory has taken a new form. Now, according to this theory, light waves are electromagnetic transverse waves. And according to this wave nature of light, we are going to discuss initially about the concept of interference. To know about the wave theory of light given by Huygens, let us consider first of all what is the wave principle which has been predicted by Huygens. Huygens wave principle. Let us first of all discuss about Huygens wave principle. What was the statement given by Huygens in terms of wave principle? Huygens said, every particle on the primary wavefront that behaves as a secondary source of light and will emit secondary waves which travel only in forward direction. Every particle on the primary wavefront, that is the concept first. What do you mean by wavefront here? Generally, we need to know wavefront is nothing other than the locus of the particles. Locus of the particles which are in the same phase. That is what we call it as wavefront. This locus, while talking about, every wavefront is going to have several particles which are in the same phase on that. Each particle again emits secondary waves. That is what has been the prediction of Huygens in his wave principle. And they emit secondary waves now. And these secondary waves always used to travel in the forward direction. That means they cannot come back till the total energy is lost or till the total energy is distributed to the neighboring particles. The wave used to travel like that only. Finally, it dies. That is a concept actually one has to understand out of this. So, if you take this locus of the particles which are in the same phase, we call that one as wavefront. In fact, when we take wavefront, there are different shapes for them we have imagined. One, of course, we used to call it as circular wavefront. And the second one, of course, we can take it as cylindrical wavefront. The third one we take it as spherical wavefront. And the fourth one here is plane wavefront. When we talk about the ripples formed on the surface of water, they are now to be called as circular wavefronts as such. When once you are throwing a stone onto the surface of water to produce ripples, if you observe this process carefully, there will be a small ripple, then the size increases, further it increases like this, but the size of the ripple is increasing, no doubt, but the amplitude of the particle which is vibrating in each ripple, that gradually decreases. So whatever the wavefronts you are having here, are observing here as a circular wavefronts, if you take several wavelets will be having here, the particles which are having the same phase, when you join them all, we get a circle like, that is what is called a circular wavefront. Now if you look at the second one, a plane object or a cylindrical object or a straight object like a tube light, that gives us cylindrical wavefronts. In fact, a point source in space, for example, if you imagine a point source in space, that is a three-dimensional one which we have to look into. Several circular wavefronts around that we can imagine in different orientations. So ultimately, the effective shape that we can imagine around that is going to be spherical wavefront. So a point source in space, that gives us a spherical wavefront. Similarly, the waves which are reaching the earth from infinite distance, for example, when we consider the sunlight, the waves which are emitted by sun in the form of waves, light waves, those waves when they travel infinite distance to reach the earth, then automatically we find that those wavefronts are planar, like plane wavefronts like this. So wavefront is purely an imagination, and out of that different types of wavefronts Huygens has just explained. One is circular wavefront, cylindrical wavefront, spherical wavefront and plane wavefront. The ripples formed on the surface of water, example for circular wavefronts. Any cylindrical object or a straight source of light, that used to give us cylindrical wavefront. A point source in space, that used to provide us a spherical wavefront, and the light whatever is reaching the earth from infinite distance, like from the sun or the stars, definitely that provides us a plane wavefront over here. So this is what is called a wavefront. Fine. But what is the principle given by Huygens? Every particle on the primary wavefront behaves as a secondary source of light and will emit secondary waves, which of course used to travel only in forward direction. They move forward, they will never come back. Now in this particular statement, there is one more term which we are coming across, that is called secondary wavefront or secondary waves. What are these secondary waves? In general, the waves which have been given by primary source, they are to be called as secondary waves. When we take a general example this way, when a person is just reading physics at around 11:30, 12 in the night, sitting in a room, when the power is put off, then immediately he cannot just rush up to get a torchlight or anything like that. Reason is better known to all of us. As and when the power is off, complete darkness we find around. But what exactly happens if you just wait for 3-4 minutes there? Then automatically, even in that darkness also, you can just be able to see where the torch is kept. Of course, you may not be able to read the physics book again in darkness. That is a different issue. But you surely be getting the path where exactly you have to go to get a torchlight or any other bulb, any other source of light as such. So this is what actually we have to take up as general example. What might have happened in this case? Light, of course, in your locality might be off, but light at some other place may be there. The light waves which are entering into your room, they now will be multiplied by means of secondary waves. Those secondary waves will make you at least see where the torch is kept even in that darkness. So this particular example, when we consider, the wavefront or the waves which are being produced by primary source of light, they are now to be called as secondary waves. And the wavefronts which are being formed thereafter, they are to be called as secondary wavefronts. Now, according to Huygens Wave Principle, every particle on the primary wavefront behaves as a secondary source of light and will emit secondary waves which travel in forward direction. So, this is actually the statement by means of which he has just explained that light is going to have wave nature, not the particle nature as said by Newton. But considering this particular wave nature of light, how to just identify the velocity of light in a particular medium? How to just calculate the wavelength of light in a particular medium? All these calculations we can make it out by considering the same wave principle which has been given by Huygens. Let us take up the concept of refraction of light considering wave principle given by Huygens. Let us consider this is a line which is separating two different material media. Above this one, we have a rarer medium, and down below this one, we have a denser medium. Let us even take up the refractive index of rarer medium as mu1, refractive index of denser medium as mu2. And we shall understand this way now, a wavefront is just entering from rarer medium into a denser medium. That wavefront, I just draw it like this. This is the wavefront. It is just advancing like this and striking the plane or the surface, which of course is separating two separate material media. Now, the moment it strikes here, a part of that wavefront now will be bending towards the normal while traveling through the second medium. That in the sense we can say refraction is taking place. Due to that refraction of light, this is the way the wavefront used to travel in the second medium as such. When we consider this point as A, we consider this point as B, then one perpendicular if I draw here and one more perpendicular if I just draw that one from the point B, and if I name this point as C and name this point as D, then we can straight away understand from this figure this angle is called angle of incidence and this angle is called angle of refraction, that is R. This is I. Not only that, one more point we can understand distance between two successive wavefronts, that we call it as lambda. Now even here also, distance between two successive wave fronts, that we can call it as lambda. Let us take this lambda as lambda 1 and this wavelength as lambda 2. Now it is just entering from a rarer medium into a denser medium this way. This being angle of incidence, this being angle of refraction, now I apply Snell's law for this system. According to Snell's law, refractive index of denser medium with respect to refractive index of rarer medium, that now is going to be sine of angle of incidence divided by sine of angle of refraction. In fact, mu is equal to sin I by sin r is the formula, what we call it as Snell's law. So now in this particular case, refractive index of denser medium with respect to refractive index of rarer medium will now be sin I by sin r. Now just look at this triangle ABC. What is the value of this sin I now? It is opposite by hypotenuse. Opposite side is BC, that can now be written as lambda 1 by hypotenuse for the triangle is AB. So opposite side by hypotenuse, that is sin I. Take this as R. From this triangle ABD, what is sin R? Opposite side again, that is AD. AD is nothing other than the distance between two successive wavefronts, which is also called wavelength there. So I can write this wavelength as lambda 2 divided by hypotenuse again is AB. So what is it we are getting ultimately? Mu denser by mu rarer. But we know pretty well mu denser is given as mu 2. Mu rarer is given as mu 1. That is now sin I by sin r according to Snell's law. This is now equals to lambda 1 by lambda 2. This is the outcome. According to wave theory, refractive index of denser medium with respect to rarer medium in terms of wavelengths, it is equal to lambda 1 by lambda 2, which we can take it as lambda in rarer medium divided by lambda in denser medium. From this one, what are the conditions we can understand? The very first one, lambda is inversely proportional to refractive index. More the refractive index of the medium, lesser the value of wavelength of light in that medium. For example, when we consider air, water and glass, three different media, in which material medium wavelength of light is greatest? It is obviously air. Next to come is in water. Least of all will be in glass. So the moment we people understand that the value of mu is increasing, automatically wavelength decreases over there. And what is the second observation? This value of lambda is inversely proportional to mu is 1, and value of lambda is directly proportional to velocity of light in that medium. What for also you can understand here? This lambda 1, you can rewrite it like this. Lambda is equal to C1 by nu by C2 by nu. Nu being the frequency which is constant, that gets cancelled, and you are now left with C1 by C2 also. That in other words, we can say wavelength and velocity in a particular medium of light are directly proportional to each other. more is the wavelength in a medium, more will be the velocity of light in that medium. And coming to the third observation, that is how this mu and velocity of light are related. You look at velocity of light in any medium is inversely proportional to the value of refractive index of that medium. If mu is more, the value of velocity of light in that material medium automatically will be reduced. So one of the examples we can take up like this. Velocity of light in air is 3 into 10 power 8 meter per second. Same way, velocity of light in water is going to be around 2.25 into 10 power 8 meter per second. Whereas velocity of light in glass of refractive index 3 by 2, its value will be 2 into 10 to the power 8 meter per second. So three different values you can directly imagine. The very first one, when velocity of light in air, that is 3 into 10 to the power 8 meter per second. What is velocity of light in water? That is around 2.25 into 10 to the power 8 meter per second. What is the refractive index of water here? We have to remember 4 by 3 standard value. Likewise, what is velocity of light in glass? That will now be 2 into 10 to the power 8 meter per second. And what is the value of mu of glass now? It is around 3 by 2. So these are the values which directly you can remember. So ultimately, by considering the wave principle given by Huygens, one can prove that wavelength of light in a medium is inversely proportional to the refractive index of the medium. That is the first point. Wavelength of light in a medium is directly proportional to velocity of light in the same medium. That is the second point. Similarly, the third one, velocity of light in a medium is inversely proportional to refractive index of that material of the medium. That is the third point we have to remember. All the three, by considering wave principle of Huygens only, we have just derived, and these results are to be remembered.